Hi everyone, in this video, I'll be showing you how to run a chi-squared test for independence, which is a test which allows us to determine whether two categorical variables, also known as qualitative variables, are independent or associated. And so to learn about the chi-squared test, we'll be working with the example we see here, in which we'll seek to determine whether or not personality styles are independent or associated to artistic preference. And put simply, there's a lot to cover. Indeed, we'll start by learning how to state the null hypothesis as well as the alternative hypothesis. We'll see how to calculate the expected frequencies. I'll then be showing you how to compute or calculate the chi-squared statistic by hand. We'll then see how to determine the degrees of freedom that we have, as well as how to use that value alongside the significance level chosen to find the critical chi-squared value. And of course, we'll finish by seeing how to draw our conclusion for our chi-squared test for independence. So as you can see, there's a lot for us to cover here. And my intention in this video is to teach you the entire process step by step with every single bit of detail, so that you'll hopefully walk away from this video knowing how to do a chi-squared test on your own. So let's get started. On the screen here, we can see that we're given the observed frequencies for personality styles and artistic preference, where each of the personality styles makes up for one column, and each of the artistic preferences makes up for a row. And the table we see here is known as a contingency table. And so typically, this is the type of table we may end up with following a survey that we may send out. Now, the first thing we need to make sure of here is that we add the totals to our contingency table. And so for that, I'll add a totals row as well as a totals column. And so I'll start with the totals row at the bottom here. There we go. I'll quickly write totals. And I'll extend each of these columns just a bit. And so here at the bottom of the creative column, I'll write up the total, which is 12 plus 6 plus 2, which is 20. And I do the same at the bottom of the analytical column, so that's 8 plus 4 plus 6, which is 18. And of course I do the same for the last column, the adventurous column, so 3 plus 10 plus 9, which is 22. And at the very end of the row, I'll add the total that makes. So that's 20 plus 18 plus 22, which is 60. Next, on the far right-hand side of my contingency table, I add a totals column. And so I'll extend the rows here. There we go. And so here I write the totals of each of the rows that we have. So the total number of people who preferred realism would be 12 plus 8 plus 3, which is 23. Those who preferred abstract art, well, that's 6 plus 4 plus 10, which is 20. And last but not least, those who preferred pop art, well, that's 2 plus 6 plus 9, which is 17. And a quick check I recommend you always do, even though we know the total number of people surveyed here was 60, is to make sure that the totals that we have on the right-hand side here also add up to 60. So in this case, that's 23 plus 20 plus 17, which indeed adds up to 60 as well. Had that not been the case, then something must have gone wrong and we should check our calculations again. That being said, I carry on. As soon as our contingency table is finished and looks like this, the first thing we should always do is state the null and alternative hypotheses. And the null hypothesis we write with a capital H and a subscript 0 like so. And this null hypothesis will always be that the two categorical variables that we have are independent. So in this case, the two categorical variables we have are personality styles and artistic preference, and so our null hypothesis will simply be that personality styles and artistic preference are independent. And so I'll quickly write that here. Personality styles and artistic preference are independent. The alternative hypothesis, therefore, which we write capital H with a subscript 1, well, that will be that the two categorical variables that we have are not independent. And a word we'll often use to say that is the word associated. So our alternative hypothesis will be that personality styles and artistic preference are associated. And so I'll quickly write that as well. Now just one word about the null hypothesis. Put simply, when running a chi-square test, the null hypothesis is what we're assuming to be true. And in many ways, this statement is our starting point. And when we run a chi-square test, which we're about to do, we're effectively checking whether or not the data we have gives us enough evidence to confirm that this assumption is true, or whether we have to contradict the assumption and accept the alternative hypothesis. That being said, I carry on. The next thing we have to do, and I'll write a little 2 right here, is to find or calculate the expected frequencies. And to do that, we'll make a quick copy of the contingency table that we have here, but we won't copy the observed frequencies we have inside this table. So let's see if I make a quick copy, something looking like this. We have creative, analytical and adventurous, and I add the artistic preferences. Okay, so the idea behind this table is that we're going to be filling in each of these cells with the frequencies we would expect to see if our 2 categorical variables, so artistic preference and personality styles, are independent. And my objective in this video is to show you the mechanics of how to compute each of the numbers that goes inside this table, and I'll explain the theory behind it in a separate video. So let's go ahead. Looking at the table we see here, we can see that we have 3 rows and 3 columns. And if I think of these as row 1, row 2, row 3, and column 1, column 2, and column 3, I can refer to any one of these cells using those names. For instance, this cell right here would be row 3, column 2, or this cell right here would be row 1, column 1. And now to calculate the number that goes inside this cell, so that's row 1, column 1, I multiply the total of row 1 by the total of column 1, and I divide that by the total number of observations. So let's see, that's 20 times 23 divided by 60, which is equal to 7.67, where I'm rounding to 3 significant figures. So I'll write that here, 7.67. For the next cell, we're in row 1, column 2, so I multiply the total of row 1, which is 23 again, times the total of column 2, which is 18, and I divide that by 60. So that's 23 times 18, and I divide that by 60, which gives us 6.9. That's why I enter that here. There we go. That's 6.9. I carry on this way. For the next cell, we're in row 1, column 3, so that will be 23 times 22 divided by 60. So that's 23 times 22 divided by 60, which is equal to 8.43. So that's 8.43. And I now move on to the next row. So here we have row 2, column 1. So that's 20 times 20 over 60. If I quickly type that, that's 20 times 20 divided by 60, which gives us 6.67. That's 6.67. And I carry on this way. Row 2, column 2, well, that will be 20 times 18 divided by 60. So that's 20 times 18 divided by 60, which is 6. I carry on. For the next cell in row 2, column 3, that would be 20 times 22 divided by 60. So that's 20 times 22 divided by 60, which gives us 7.33. We're nearly there, and I finish with the third row here, so that's row 3, column 1. So I take the total of row 3, which is 17, times the total of column 1, and I divide that by 60. So that's 17 times 20 divided by 60, which is 5.67. I carry on. Row 3, column 2, so that will be 17 times 18 divided by 60. So that's 17 times 18 divided by 60, which is 5.1. And last but not least, row 3, column 3, so that will be 17 times 22 divided by 60. So that's 17 times 22 divided by 60, which is 6.23. Okay, we now have our table of expected frequencies. And so just to be clear, I like to write EXP here for expected, and I write OBS here for observed. Okay, so the values in our contingency table are what we observed, and the values in the expected table are the values we would expect to see if our 2 variables were indeed independent. And so our next step, step 3, is to calculate or compute the chi-squared statistic. And the formula for doing that, I'll write chi-squared with a little stat underneath that. There we go. That stands for chi-squared statistic. Well, that's equal to the following. For each of the observed values we have in our contingency table, So for each one of them, and I'll write O here for observed, we're going to subtract its corresponding expected value. And so I'll just write minus capital E for expected. We'll then square that result, so O minus E squared, and we'll divide that by the expected value, E. And here's what this would actually look like. For the observed value 12 that we have here, its corresponding expected value is a 7.67 we see here. So we would do 12 minus 7.67, that's the O minus E we see here. We would then square that result and divide that by 7.67. That's the expected frequency which corresponds to this observed frequency. And we'll have to do this calculation for every single one of the observed frequencies and add all the results we get together. And to indicate that we'll add all the results we get together, I write a large sigma, meaning sum, at the front of it all. And that's a very important formula, so I'll go ahead and box all of that. There we go. Okay, well, as you can probably guess, this will be quite long, but it's something we need to do. So I'll go ahead and write chi-squared stat, and now let's get started. So for the first observed frequency, that's 12, we'll do 12 minus 7.67 squared over 7.67. So I'll write that out. That's 12 minus 7.67 in parentheses squared over 7.67. I carry on. Our next observed value is 8, so we'll have 8 minus 6.9 in parentheses squared. So that's 8 minus 6.9 in parentheses squared divided by 6.9. I carry on. For the next observed value, we have 3. So we do 3 minus 8.43, and we square that as well. So that's 3 minus 8.43 in parentheses squared over 8.43. And I can see right away that I won't have enough space to write it all out on one line. So I'll already spread this over several lines. So I add to that our next observed value, which is 6. So that's 6 minus 6.67. So that's 6 minus 6.67 in parentheses squared divided by 6.67. And I carry on with the next value, so that's 4. So we have 4 minus 6. So that's plus 4 minus 6 in parentheses squared divided by 6. And we carry on. We have 10 as the next observed value, so that's 10 minus 7.33. So that's 10 minus 7.33 in parentheses squared divided by 7.33. And I'll write this over one more line here. We add to that the next observation, so that's 2 minus 5.67. So I do that in parentheses, 2 minus 5.67 in parentheses squared, and I divide that by 5.67. And I add to that the next value, so that's 6 minus 5.1. So that's in parentheses 6 minus 5.1 squared divided by 5.1. And we add to that what we get for our last observed frequency, 9. So that's 9 minus 6.23 in parentheses squared. So that's 9 minus 6.23 squared divided by 6.23. And after typing all of this on my calculator, which I won't do in front of you here to save a bit of time, I find that the chi-squared statistic, is equal to 11.6. where I've rounded to 3 significant figures. And I'll go ahead and box that result. There we go. Now before moving on to the next step, let me quickly point out what this calculation is actually showing us. Looking at each of the terms in this long sum that we have here, we can see that each and every single one of the numerators is technically measuring how far away our observations are from the expected values. So for instance, this 12 minus 7.67 here, well, that's measuring the difference between our observation and the value that would be expected if the variables were indeed independent. And something similar could be said for each of the terms we have here. So as such, the chi-squared statistic can be thought of as the sum of all the deviations we have between our observations and the expected values. And so the further away our observed values are from what we could expect them to be if the variables were independent, the larger the chi-squared statistic we get. And so the whole idea behind the chi-square test is going to be to compare this chi-square statistic to some threshold value, The idea being, if our chi-squared statistic turns out to be greater than that threshold value, then we'll conclude that the variables we have are not independent and are associated. And that threshold value is known as the critical chi-squared value, which is what we learn how to find next in step 4. Now, to establish what the critical chi-squared value is, we need two things. First of all, we need to establish the degrees of freedom we are working with here. So I'll just say degrees of freedom. And put simply, the degrees of freedom will always be equal to the number of rows we have, so I'll just say rows, minus 1 times the number of columns we have minus 1. So I'll just say cols minus 1 for that. And in fact, I'll box that formula. There we go. Do make a note of this. Okay, and so for the table we're working with here, the number of rows we have is 3. Indeed, we have realism, abstract, and pop art, so that's 3 rows. And the number of columns we have, in this case, is also 3. We have creative, analytical, and adventurous. So the degrees of freedom we're working with here, which we often just write df, will equal to 3 minus 1 times 3 minus 1, which of course is just equal to 2 times 2. In other words, the degrees of freedom we're working with is equal to 4. And I'll go ahead and box that result as well. There we go. The next thing we need to determine the critical chi-squared value is the significance level that we're working with. And the significance level we'll come across most often will be 5%. And so for the chi-squared test we're running here, I'll go ahead and choose that significance level, which is 5%. And so I'll quickly write that here, significance level, which we'll often refer to as alpha. So in this test, we're saying that alpha is equal to 5%, which as a decimal is 0.05. And I'll go ahead and box that as well. There we go. Now, a quick side note about significance levels. Put simply, the significance level that we choose, or that we're given in a test, is the probability that we draw an incorrect conclusion when running our chi-squared test for independence. And to be more specific than that, the significance level we choose is equal to the probability of making a type 1 error. And a type 1 error means rejecting the null hypothesis when it's actually true. And the most common significance level we'll come across will be 5%, as we took here, but we could also come across 1%, which is often used when running chi-squared tests in a medical context, and we could also come across a significance level of 10%, which is frequently used at the first stages of research, so in a more experimental context. That being said, now that we have our degrees of freedom, as well as our significance level, we're ready to look up our critical chi-squared value. And here I show you how to do that with a critical chi-squared values table, which you can see on the screen. Looking at this table, the first column we see, at the top of which is written df, corresponds to the degrees of freedom that we're working with. Here we saw that df is equal to 4, so we're going to be working with the fourth row of that table. Next, the second, third, and fourth column in that table are critical chi-squared values for different significance levels. So the first of those columns is for a significance level of 10%, the second one is for 5%, and the third one is for 1%. And since our significance level is 5%, we'll use the second of those three columns. And so looking at that column for degrees of freedom 4, we quickly see that our critical chi-squared value is 9.49. And so we can write that at the bottom here, our chi-squared critical, and I'll write CRIT, crit, is equal to 9.49. And again, I'll go ahead and box that value. Okay, now that we have the critical chi-squared value, we move on to our fifth and final step here, and that is to draw our conclusion. And to do that, we need to compare the chi-squared statistic that we calculated to the critical chi-squared value we have here. And put simply, if the chi-squared statistic that we calculated is greater than the critical chi-squared value, then we'll reject the null hypothesis. In another video where we'll be using our calculator, we'll see that we can also compare the p-value we get to the significance level we had. And working with the p-value is completely equivalent to working with the chi-squared statistic. And so to draw the conclusion for a chi-squared test, you could use p-value or the chi-squared statistic. But in this video, I'll only be focusing on comparing the chi-squared statistic to the critical chi-squared value to draw our conclusion. And so here we notice that the calculated chi-square statistic is greater than the critical chi-squared value. And I'll quickly write that there. The chi-squared statistic, chi-squared stat, is greater than the chi-squared critical, or critical chi-squared value. Indeed, in parentheses here, 11.6 is definitely greater than 9.49. And consequently, we reject the null hypothesis. So we reject h sub 0. And there we go. Okay, so since our chi-squared statistic is greater than the critical chi-squared value, we reject the null hypothesis. And what that suggests is that personality styles and artistic preference are not independent. And we therefore accept the alternative hypothesis, which suggests that personality styles and artistic preference are associated. And to formulate your final answer nicely in an exam, you would state a conclusion along the lines of what you see in the upper right-hand corner of the screen. That is, that the chi-squared statistic is greater than the critical chi-squared value, so there is sufficient statistical evidence to reject the null hypothesis and accept the alternative hypothesis, which in context tells us that personality styles and artistic preference are associated. And there we go, that's it for this rather long video for the chi-squared test for independence, and I truly hope you found this helpful. And if you did, please hit like on this video, drop a comment down below, and even subscribe to this channel to help get this video to as many students as possible. All that being said and done, that's it for this tutorial.